All right, so in this video lesson, again, I am going to give another example on how we can apply the disk method into finding the volume of a solid that is generated by rotating a given region about a given axis. However, this video lesson is highly recommended to be watched after you have seen enough of my other video lessons where I gave examples on direct calculation of how we apply the disk method into finding the volume of a rotated solid, I mean of a solid that's generated by a rotated region. Because this example by itself I'm about to show right here is not as a direct application, I mean not as a direct calculation problem anymore. Okay, and so allow me to bring up the problem with the wording of the problem, and you're gonna understand the intention of the problem right there. So we are still going to apply the disk method, but then we're not applying that as a straightforward computation problem, but we are applying it in a much more creative style, in a much more creative approach like that. And that hopefully push your understanding, especially for students who are on track for advanced career that involves advanced math like that. Okay, and especially math major, that can, this example can enhance your understanding and broaden out your understanding, okay, and of how you can use calculus and especially and particularly the disk method into solving a problem. Okay, and so now let me bring up on screen the wording of the problem. All right, so here we go. One very short problem right here. We want to prove the formula for the volume of a sphere. Okay, volume of a sphere. So yes, definitely we are in any of these problems here, then we are looking at how to calculate a volume. But now we want to prove. So prove the formula for a volume of a sphere. Okay, so that puts into our concern here. Let's remind ourselves a little bit. What is the volume of a sphere? Okay, so volume of a sphere. High school geometry students learn that volume of the sphere is a 4/3 pi or cube. Okay, so a couple explanation. Sphere is a nice round sphere, like a nice round ball right there, like a basketball or a volleyball or any kind of ball shape. It's a sphere, okay, formally speaking, or a three-dimensional circular shape right there. Okay, and so it's completely round around. So from the center of the sphere out to the sphere surface right there, that's what this radius is. So this length right here is called the radius. So here we go. This is the volume formula for, this is the formula for the volume of any sphere, okay, at any given radius right there. Volume equals 4/3 pi times r cubed. So now all of a sudden, as I brought up this formula, then anyone viewing the video is feeling so familiar with this formula. Okay, so the point of this problem now is that, so yes, we have been using this formula so fluently, but now how did this volume formula come out? How did the ancient mathematician come up with this volume? And so, as a matter of fact, calculus was a more modern math. So here we particularly want to apply calculus, and particularly the definite integral, and even more particularly the disk method into proving this. But the method I'm about to show you here is the calculus, the more modern method to prove this formula. It's not really the ancient proof that proved this formula, because the ancient mathematicians already proven this formula thousands of years, even before long before calculus came around. Okay. And so here so the point now is that proof just means how did this formula come to us? How did this formula become the truth right here? So that's why we want to get it proven. But we are going to prove this using the disk method, using calculus generally. Okay. All right. So now the situation here we have is just simply a sphere of any given radius r. And now for anyone viewing this video, I assume that you are more mature than just or has to be a 3 or has to be a 4. Radius of the sphere has to be 2 or 1. I want you to be more mature than that. The radius here is generally a radius r. So how does that come out? To be volume of a sphere to equal 4/3 pi times r cubed. And that's what we're trying to answer right there. Okay. All right, so now allow me to erase the notes here. And all I know now is that we're having a sphere. Okay, we're having a sphere, and this sphere here has a radius r. That's all we know. Okay, that's everything we know. So now, as I mentioned, we are about to use the disk method to prove the volume. And this example is one among the examples where I want to show that we're attempting to find volume of those solids that's generated by rotating a region. So that means before we can get started into anything, we definitely want to see how this volume here, how this solid as a sphere here came out as a rotation of some given region. Okay, so again, let me repeat that. Before we can get our hands on proving the formula or whatsoever, we have to see, first of all, how this sphere here comes out or came out as the result of rotating a given region around a given axis. Okay, so now in that reason, allow me to get over to my computer screen right here and the graphing calculator with decimals. All right, so here we go. So now assume that this is a sphere. Nice round ball right here. Okay, and then it's already the version of the sphere where we had some complete rotation, and that's why I have a nice round sphere right here. Okay, so now allow me to show this demonstration. Allow me to sort of like use the software to undo the rotation. So now I'm gonna undo the rotation, and so observe closely the motion of my work undoing the rotation. So as I completely undo the motion, then now all of a sudden we realize. So it comes out that, as we realize now, that the volume of a sphere or any sphere really came out from rotating a semicircle region, a semicircular region around a given axis. And so obviously in this case, for simplicity, we can just rotate this semicircular region around the x-axis, and here we can, in a 3D perspective right here, this is my x-axis, this is my y-axis, and then this is the third axis in a 3-dimensional setting right here. But now, see, as we rotate this semicircle, this region bounded by the semicircle here between the x-axis, okay, and that upper half circle and that semicircle above the x-axis here, then rotating that bounded region, we are obtaining a sphere. Okay, or my point again is that undoing that rotation work right here, then this sphere really came out from rotating a region that is a semicircular region right there. Okay, and we can put that diameter side of that semicircle right alongside with the rotation axis. So in a flat view, think about it, we're placing our eyes to look straight at that wall right here, to look straight at that region right here. As a standing wall, then the region looks as following. There is our semicircle, okay, the semicircular region right here. All right, and so now for simplicity, even though we can also seat, so in my wording here, we can put this, we can position this, or we can seat this region anywhere in the x and y axis system, but for simplicity, it's the easiest case, which does not alter the proof at all. The easiest case here, since the circle itself is quite symmetric, any circular region is quite symmetric, so I can put that region to be symmetric right around the y-axis here and seat it right at the origin right here. And to make the problem simpler for us, and it won't alter any of our work at all. Okay, and so in that reason, now I can see that it's a half circle where the center is right at the origin 0, 0. So this curve here is a half circle. The region is defined, is bounded between the x-axis, the upper semicircle, okay, and the region bounded there. But the upper semicircle, the semicircle itself, or the complete circle itself, is centered at the 0, 0. And then so the radius is wherever the radius is the distance that comes out from the center of the circle out to anywhere on the circle itself right there. So that means consequently in this picture over here, radius is how big this distance from the center either out to this way or out to that way. Okay, and so this distance right here is my radius. All right, and so now I'm going to get back to the board, and once we have seen a clear picture and hopefully that helped our imagination, then now we're going to focus strictly on that semicircle region, okay, that semicircular region before rotation. And let's look more into that, and let's see how we can bring some math in there. Okay, so now I'm going to erase this picture. All right, and so now here's my x and y axis system. And again, we don't need to worry about whether r, the radius, has to be 2 or 3 or 1. It's just any general r value. Okay, so that means we have a semicircle here, and of course, forgive me that I can't make the semicircle as perfectly drawn as the way how it's done in decimals right here. Okay, but now in this way right here, and 0, 0 is right at the center right here, and that indeed does bother me a little bit. That I'm drawing that a little off right here. Okay, but so in the way how it is, then numerically speaking, and here's our x-axis, which eventually will become the center of rotation. Our region is here. Our semicircular region is here. And so in that way, think about it. If the circle has radius or if the sphere was initially given to have radius or, then, and that's the sphere came out because we're rotating this region. So that means this circle here, where the center is here, has to have also radius r. So if this is r right here, then 0 on the x-axis, then come out here, yes, it's r, but come back out here, the ending here has to be a minus r. Like that. Okay, the ending of that region, the left end of that region is a minus r. Okay, and so now again, once we have nailed down the picture here, the flat 2D version before the flat 2D region before rotating it around this rotation axis, then now let's set out for ourselves, let's align ourselves back into the usual work. We're gonna imagine that we place our eyes to look straight at that center of rotation. Okay, the center of rotation, the axis of rotation is the x-axis, and so now then in that ways, any stripe that's drawn perpendicular to the rotation axis and drawn to reach and ends at so it's drawn from the perpendicular to the rotation axis and it's drawn to reach and end at the boundary of the region itself right here. Those are stripes right here. Any of those stripes after being rotated will create a disk for us, a circular disk for us. And so in the way how our eyes is looking back straight at it, then those stripes right here rotating it will give us a disk. Okay, so just like that, the stripe is going like this. So if this is your axis, then the stripe is creating a nice disk. Okay, and so now extracting a disk out, and we can have a disk like this, where center of rotation coming out here, or axis of rotation comes out that way. So the thickness, this is going to be the thickness. Okay. All right. So in that way, now I back again to that fundamental I have introduced in a general lecture about the general discussion lecture about the disk method. Then the ultimate thing we need now is, first of all, for any disk or regarded as a cross section, then on any disk there we simply need to find the cross section. Okay. For any disk, we just simply need to first know what the cross section is, cross section area, and then we multiply the cross section area with the thickness. Okay. Doing this will give us the volume of one infinitesimally thin disk, and then we are going to accumulate all of those disk volumes from a start, okay, to an end, like that. Okay, from a start to an end. All right, so that exact same fundamental I've been pointing out since the general discussion lecture and throughout many examples before this particular one right here. Okay, and so now in that way, once again, back to what I was explaining, back in the style, how I approach and deliver that in a general discussion lecture, then I highly recommend to find the thickness, okay? Because I really don't recommend any of my students to remember formula. So thickness of any disk, in a way how it's placed right here, again, in a scratch picture, okay? A disk looking like that, okay? And thickness. So this is the x-axis, and if we call this the thickness right here, then that much space is how much change, the infinitesimally small change in x, where we call that is a dx value. Okay, so in that way, clearly thickness is found to be dx. Okay, and now once I have found thickness to be dx, and now it will become our d expression, our differential expression in this the formula for the integral right here. Then, okay, then so cross-section area, I haven't found that formula yet, but thickness now I have found that to be dx. So that means that leads to concluding or deciding that the cross-section area must be a function in terms of x, because I have explained many times throughout any of my integral video lecture that the main variable of our integral function, okay, the main variable of our function in the integral here must be consistent with the variable indicated in the d expression here. So in the d expression, it's a dx. So the main variable has to be x, the main variable of the function. And so now the cross-section area, we have to find our way to create that cross-section area as a function of x. Okay, so now let's find out about the cross-section area. Okay, so cross-section area. So again, the cross-section is simply just the disk that's generated by rotating any of our stripes perpendicular to the x-axis, the rotation axis, but right through the limit, right through the rotated region and stop and end right at that region boundary right there. Okay, and so that's the disk. And so now area of any disk like that, or any cross-section like that, is pi r square in this case, because again we're having disk shape like that. But now if we realize again in this picture, in this region before rotating it, then this region here, we can treat that curve here as a function of x. Okay, because the stripe here, the height of the stripe changes. The height of the stripe here is lower than that height of the stripe here, and different from that height of the stripe here. It all depends on where we have our x value at. And so now it makes sense that we treat those heights here, which is now also the radius of the disk. The radius. Now this r right here is not the same as that r. Okay, so maybe I should have used a lowercase r. How's that? Just to indicate that any disk right here, when we're rotating that, the radius here is the radius of the disk when we're rotating it, not the radius of this big semicircle picture. Okay, and so now again back to what I was trying to explain. Now I see that this stripe right here, or the radius of the consequently generated disk as a cross section in front of our eyes here. Then that radius there comes out, seems to be like the height or the function output of wherever the x value is at that x value, okay, onto this function. So now we need to find out a way to find out what is the f of x function that has this curve as a semicircle. That's the key point right there. Okay, and so now I am going to swing to the other side of the board and let's derive the work a little bit. So anybody learning calculus, up to learning calculus, is well familiar that anytime we're having a circle, regardless of what radius that is, whatever radius that is. So I should have, or how about let me indicate, so radius r, but in a special case where you purposely put your circle to center at 0, 0, then any circle, it's a graph, strictly mathematically speaking. Any circle, once we draw that, it's a graph. Okay, and now specifically in this case here, if once we're putting that at the origin, the center of the circle right at the origin, then this circle has the famous equation x squared plus y squared equals r squared, where r here is the radius of the circle given right here. And allow me not to go too far back into remind anyone about this. Okay, but so now x squared plus y squared equals r squared. It's just simply an equation of any circle center at 0, 0 with given radius r here. But now, since we purposely want to look at this circle as we only want to look precisely at half of that circle, or we only want to look at the semicircle above the x-axis, okay, and we want to look at that curve here as an expression in terms of x, we want to see this curve as a function of x somehow. Okay, so that means now we have to bring back some of our algebra understanding. We're going to have to solve from this equation, we're going to have to solve for y as a function, as a variable that's dependent on in terms of x. Okay, so but it's going to be simple work enough. We're going to subtract our x squared from both sides. Okay, so that produces for us y squared equals r squared minus x squared. That's the first step. And we are on our way to extract out the y variable as an expression in terms of x here. So the right hand side, the opposite side is already completely in terms of x already, but the left hand side is still a y squared. So we have not solved for y yet. So only one more step. I am going to take the square root of both sides. So that's why on the left hand side it becomes just the y, but taking the square root on both sides, remind yourself, you will always need the plus and minus square root. Okay, so we're going to take now square root of r squared minus x squared. Okay, but then wait a minute. Doing this, then we're going to end up with two curves. And yes, ladies and gentlemen, the truth here is that when we're taking the square root on both sides to solve for the y variable as an expression of x, we actually don't end up with one expression of x. We end up with the same y variable equals two expressions of x. One of them is positive square root of r squared minus x squared. The other one is y equals negative square root of r squared minus x squared. We have two expressions in terms of x that the y can be equal to. So in this case, how do we know which one we need to choose for our particular problem? So I purposely made that a heavy bold line right here. That means here this is the part where our y value has to be positive, because it's the upper dome that I chose. It's the upper semicircle that I chose, the upper dome. Okay, and so in that way, now back in this solving work right here, then now we're clear that we're gonna choose y equals r squared minus x squared. That's the appropriate one. That's the correct one for the situation we're at. Okay, and so now that means back in my area of the cross section formula here, the area of that circle, once we're rotating it, once we're rotating any stripe height right here, then it's the height there becomes the radius of the rotated the cross section. And so area equals pi r squared. But that means the area of the cross section equals pi times, but r now is found to be the square root of capital R. So capital R squared minus x squared in the square root, but that's radius of the, so any height here is square root of r squared minus x squared. Okay, and that big R is here. This big part right here is the big R. Okay, and so now in that way, I'm going to square that. So that gives me the area of the cross section completely in terms of the x variable. The R here looks a little threatening. The R here, the R letter here looks a little threatening, but it's just, now in this function itself, the R is acting as a constant term, because once the radius here is given, it stays the same for the entire circle. We can't change that radius unless we're in a different problem. Okay, and so in that way, now the area of the cross section is pi times square root of r squared minus x squared, but then square. Okay, so now in that way I'm looking at pi times square root of r squared minus x squared, but then all of that square. And now I have successfully formulated my cross-section area as a function of x and y as a function of x, because our d expression here initially recognized to be in terms of x. It's a dx expression here. Okay, and so now again back to the picture as I have explained at the end of my general discussion lecture on the disk method. Then see, and here we are rotating around the x-axis, the horizontal axis, and of course our disk here are those disks perpendicular with the x-axis, or disk that's standing straight up like this. And so in that case we are thinking about, visually speaking, we are accumulating those disks from the left to the right. Okay, once we have created the solid, and then those disks right there, we're accumulating those disk volumes from the left to the right. That's our start to our ending of the accumulation. Okay, so that means now I have a clear picture. This integral, I'm going to proceed from x equals minus capital R to positive capital R. And this is now our complete setup of the integral, of the definite integral that will get us the final volume of this sphere once we rotated that shaded region right here. Okay, all right, so now in that way I am going to navigate to my next board right there, and I'm going to use all that space right there to complete my work. All right, so now as far as the integral from the other board right here, allow me to rewrite that here. The volume as a complete integral is an accumulation from minus r to r, pi times square root of r squared minus x squared square dx. But so now, before I can even take the definite integral, and do not feel so threatened about instead of having it like a minus 1 to 5 or a negative 2 to 2, something like that, we have just abstractly a minus r to r, but in the end see this as some value, some negative value, some positive value, and these are all constants. Okay, so there shouldn't be anything to worry about. And again, anyone viewing this video lesson should be at the calculus level where your mathematical understanding has become a lot more mature already back compared to those days when you were still in algebra course. Okay, so believe in yourself about this. So now the square will cancel with the square root, definitely, and then at the same time I see that this is a constant coefficient to the function, so we can pull it out front. So in my next step, allow me to do two things in one step right here. Okay, it's still the integral accumulating from minus r to r, but the pi is being brought out front as a constant coefficient multiplied with the integral. And then the square is going to cancel with the square root, leaving behind for me just simply r squared minus x squared dx. Okay, and so at this point again, you see, I had a short video lecture where I discussed, where I clarified the idea of why it's so important to have the dx here, because you see now in an integral like this, where we're working completely without numbers, then we see a whole bunch of letters. This is a Greek letter for p, but we call it pi, but it's a Greek letter lowercase p right here. And then this is letter R, and letter x. So see, out of a definite integral with a whole bunch of letters like this, the dx here is indicating clearly for us that only anywhere you see the x, that's your variable. The rest, these are all either constants or a coefficient. Okay, and so now that means it's making things easier for us. Now, fundamental theorem of calculus now says that we can just simply find the antiderivative of this function as a function of x in respect to x. Okay. And so now I'm going to have pi times, if the first term is simply just a constant, then taking the antiderivative, it gives me r squared x. And the next term here, initially with x squared with a minus in front, so now it's going to become minus 1/3 x cubed. Okay, that's our successful antiderivative. And now we're going to need to evaluate this according to, and allow me to rewrite this in a more space logical way right here. So pi times r squared x minus 1/3 x cubed right there. And then we're going to evaluate this from minus r to r. At least I saved myself a little bit more space right there. Okay, and so in that way, now once again, we only, even though there are a lot of letters here involved, but we just need to only focus on the x variables, because that's our main variables, our main variable of the entire antiderivative function right here. Okay, and so in that way, now this is how I'm seeing it. Fundamental theorem of calculus. Now, if this is a straightforward computation problem, then I can go a little loose in terms of substituting in, but now this is completely a problem where we only see letters and letters, then allow me to move on carefully with the subtractions. So be patient with me. I mean, allow me to move on carefully with the substitution step right there, where I can carefully substitute the letter r and the minus r into our function here. Okay, so be patient with me right here. All right, so now I'm looking at pi times r squared, but the x now is substituted by an r, okay, and minus 1/3 times r cubed. Okay, so should have used brackets here. So that's my antiderivative evaluated at the upper limit. Okay, and I'm subtracting. Okay, I'm subtracting, and then there's pi again. My antiderivative is r squared. Okay, but times now x is substituted by minus r, the lower limits of our integral. So minus r. Okay, but it's the same now. It's essentially the same r. These are the same r. It's just it's a minus r here being substituted into the expression, and then minus and 1/3 times minus r cubed, and that's my antiderivative substituted minus r into it. Okay, or the antiderivative evaluated at minus r. That's what it is. Okay, and so now in the next expression, we're gonna just algebraically collect all these like terms and all that, and then I'm gonna simply distribute out the pi into each of my terms here as well. So here I'm looking at pi r cubed. We're starting to see some pi r cubed. Okay, this is r cubed. So pi, so minus pi over 3 r cubed minus pi r cubed over 3, or 1/3 pi over 3. How about that? Minus 1/3 pi r cubed. So it's the same like term, it's just different coefficient. Okay, and then now in the that's done with the first group right here. Now be careful with signs. That's all. Minus pi multiply with this. But hey, there's another minus here. So minus pi times minus r. So altogether it's a plus for that term right here. After distributing that minus r, we're looking at plus pi r cubed. Okay, and now minus pi times with all this here is going to give me another minus. Okay, another minus pi r cubed, and actually 1/3 pi r cubed. Okay, 1/3 pi r cubed. All right, and so now we're gonna just simply combine, because these are all like terms. They're all like terms. It's just different by the coefficient. So these two like terms are 2 pi r cubed, and then these two combined together minus 2/3 pi r cubed. And so added it and subtracting it all together, we're looking at 4/3 pi r cubed. Okay, after doing the combining like terms for all of these 4 terms here. All right, so now, ladies and gentlemen, what was our goal initially? Our goal is to find out why or how volume of any sphere at a given radius is done by 4/3 pi r cubed. Okay, and so we started out seeing any of our sphere at radius r came out as the result of rotating a region, a semicircular region around the x-axis. So rotating that semicircular region from minus r to r around the x-axis, and of course we center the semicircle right at the origin 0, 0. And then after rotating that, we set up our integral, our accumulation work. Okay, we set up as an integral using our disk method, using the philosophy about the disk method, and then we worked out our integral, and then we arrived at the volume finally came down to be 4/3 pi or cube. Okay, and that is how we have proven this formula. And so for any of you who plan to go formally into a math major, this is the end of the proof. We got what we want. We want to find out why the volume equals that. And then we started out setting up things, and we added a proof here. So it's just a little bit of an introduction for anyone to know. So I'm going to use a little sign right here. It's a square. It's a big square, but really it's a huge period, indicating it's the end of the proof right here. Okay. So that's just a little bit to know for anyone who is going into formal math major. Okay. All right. All right. And so this problem is brought up as in the intention that it opens a door for many proving problems that can be done at the calculus 2 level for a lot of common solid shapes out there. Okay. So what is that? What is a generality of those kind of proving problems that I would like to mention here? All right, so think about at the end of high school geometry, or anywhere, at any learning point in math prior to calculus 2 right here. Then, so we have known that the sphere with radius r, okay, a given sphere with radius r has volume 4/3 pi r cube, and just now we have proven it in this particular example, okay, using the disk method. So why is it now? It's another proof that now I'm only bringing it up. I'm introducing it, and I believe viewers, after viewing my video here, can prove these formulas on your own. Okay, so what about a right circular cone? Okay, where the base here is a circular shape right here, and it has the vertex comes straight up perpendicular from where the base circle is. So this base circle is at radius r, and this height right here, this is height. Okay, so high school geometry or at any math courses prior to calculus 2 right here, we all know by heart that the volume to the formula to calculate the volume of a right circular cone like this, that volume there is a 1/3 pi or r square h. Okay, so why is that? Now with some calculus understanding, you can prove this. I can suggest seeing a cone like this as rotating a region being a right triangle like that. So the radius, the circular base, will be coming out from the radius, which is now the height, which is now the shorter leg of that triangle. So this is r right here. Okay, and the height is this much right here. Okay, and then we can think about that, setting that sideways and be rotating that region around the x-axis, and that's how we can prove. So I want to leave that on for my students. I want to leave that for viewers who just now learn from how I prove this volume of a sphere into leading you have that generality, and you can lead that into your own proof, how you prove a volume of a circular cone right here, right, to be 1/3 pi r square h. Okay, and then outside of that, we also have and as I have also pointed out in some other example, that we can realize now all of a sudden in these days we learn about solid that came out from rotating a given region. Then a lot of our known solids out there came out from rotating a given region, and as a matter of fact, a common region. So if we're rotating a rectangular shape right here around an axis, we will end up with a cylinder. Okay, we end up with a cylinder. Okay, so with cylinder, then yes, now with a cylinder like that, of course, bottom and base, if we're standing the if we're standing up the cylinder like that in the upright position like that, then this is the base and this is the top, but they all have the same equal radius r right there. Okay, so with that radius r, now this height right here is, or that length of the original drawing right here now becomes the height of the cylinder. So volume of the cylinder, of any cylinder, is pi r squared times h. Now you can also use calculus to prove why the volume of this cylinder, okay, is pi r squared times h using calculus. Okay, and so that's another picture right there for that. And so there are many other solid that came out that you can prove for the final volume, because we now know calculus, and if specifically we know the disk method. Okay.